Imagine for a moment that you are falling, not toward the ground, not through the atmosphere of some distant world. You are falling toward the most terrifying object in the known universe, a black hole, a region of space where gravity has become so overwhelmingly powerful that nothing, not light, not time, not the very fabric of reality itself, can escape its grasp. As you drift closer, the universe around you begins to change. Stars that once held their positions in the cosmic tapestry now appear to dance and swim, their light warped and twisted by forces beyond human comprehension. What would you see? What would you feel? What secrets would the universe reveal to you in those final moments? Tonight we embark on a journey that no human has ever taken, a journey to the edge of physics itself, and perhaps to the very nature of existence. Let us fall together into the dark. Before we begin our descent, we must first understand what awaits us in that darkness. A black hole is not, as some imagine, a cosmic vacuum cleaner, pulling everything toward it with malicious intent. It does not reach out and grab. It does not hunt. A black hole is something far stranger. It is a place where matter has been compressed to such an extraordinary degree that the very geometry of the universe bends around it. Think of space-time, the invisible structure that underlies all of reality, as a vast, stretched fabric. When you place a mass upon it, the fabric curves. The sun creates a gentle dip. Jupiter, a smaller depression. Even you, sitting quietly wherever you are, create an infinitesimally small indentation in this cosmic fabric. But a black hole? A black hole doesn't just curve space-time. It tears through it, creates a bottomless well from which nothing returns. At the center lies what physicists call a singularity, a point of infinite density where all the mass of the original star has collapsed into a space smaller than an atom. Smaller, perhaps, than anything we have words to describe. The laws of physics, as we understand them, simply break down. And surrounding this singularity at a distance determined by the black hole's mass lies the event horizon, the point of no return. Cross this boundary and your fate is sealed. Not even light, the fastest thing in existence, can climb back out. This is where we are going. Our journey begins far from the black hole, perhaps a few light hours away, close enough to see it, but far enough that its gravitational influence is gentle. From here, the black hole appears almost peaceful, a dark circle against the star field, like a hole punched in the fabric of night. But look carefully at the edges. Do you see it? The stars near the black hole's silhouette don't simply disappear behind it. They curve, they bend. Some of them seem to wrap entirely around the dark circle, creating a bright ring of light. This is called an Einstein ring, a phenomenon predicted by Albert Einstein over a century ago. Light from stars behind the black hole is being bent by gravity, focused like light through a lens, and sent toward your eyes from directions it never should have come from. You are seeing stars that should be hidden. The black hole has become a cosmic magnifying glass, revealing parts of the universe that would otherwise be invisible from your position. If you were to move your head, if such mundane actions still had meaning here, you would see this ring of light shift and dance. Stars would appear to swim around the black hole's edge, their ancient light traveling paths warped by gravity. It is beautiful, hypnotic, and utterly alien. As we draw closer, another feature emerges, a thin line of brilliant light encircling the black hole like a glowing halo. This is the accretion disk, material that has been captured by the black hole's gravity but has not yet crossed the event horizon. Gas, dust, perhaps the remnants of stars and planets, all of it spiraling inward at nearly the speed of light. The friction within this disk generates temperatures of millions of degrees. Matter that once drifted cold and silent through space now radiates with the brilliance of 1,000 suns. At the poles of some black holes, this energy escapes as tremendous jets of plasma, beams of light and matter shooting outward across thousands of light years. These jets can outshine entire galaxies. But most of the material in the accretion disk has a different fate. It spirals slowly inward, orbit by orbit, losing energy to radiation, until finally it crosses the event horizon and vanishes forever from our universe. We continue our approach. The stars around us now look wrong. Constellations you might have known are stretched and smeared. Light from directly behind you is being bent around the black hole and reaching your eyes from in front of you. In a sense, you can see behind yourself. The entire universe is being focused toward you, compressed into a shrinking ring of light as the black hole grows to fill more and more of your vision. And now, something even stranger begins to happen. Something that will challenge everything you think you know about time itself. Time, we believe, flows constantly. 1 second follows another, steady and unchanging, from the moment of your birth until now. But Einstein taught us something remarkable. Time is not constant. It is woven together with space into a single fabric, space-time, and like space, it can be stretched and compressed by gravity. Near a black hole, this effect becomes extreme. Imagine you have a companion, a friend in a spacecraft watching your descent from a safe distance. They have a powerful telescope trained on you, and you have one trained on them. You can see each other. You can communicate, though with increasing delay as the distance grows. From their perspective, something strange is happening to you. As you fall closer to the black hole, you appear to be moving more slowly. Not because you've changed your velocity, but because time itself in your region of space is flowing more slowly relative to theirs. For every hour that passes for you, days may pass for your distant companion, then weeks, then months. As you approach the event horizon, this effect grows ever more extreme. From their perspective, you would appear to freeze in space, your image growing dimmer and redder as the light carrying your image struggles against the pull of the singularity. They would never see you cross the event horizon. To them, you would remain there, forever suspended at the edge of oblivion, a monument to the limits of what light can escape. Your image would redshift, the light waves stretching as they climb out of the gravitational well until you faded from visible light to infrared, to radio waves, and finally, to nothing at all. But this is only what they see. For you, time flows normally. Your heart beats. Your thoughts continue. You do not feel frozen. You do not feel slowed. From your perspective, it is the universe that has gone mad. Looking back at your companionship, you would see them moving faster and faster. Their lights would blue shift, gaining energy. Days of their life would flash by in your hours. If you could watch for long enough, and if the black hole were massive enough to give you time, you might see years, decades, centuries pass for the outside universe, while only hours pass for you. This is not science fiction. This is physics. This is what Einstein's equations tell us must happen. Near the event horizon of a supermassive black hole, one containing billions of solar masses, the time dilation becomes almost unimaginable. An observer hovering just above the event horizon would experience a single year. while billions of years pass in the outside universe. They could, in theory, witness the entire future history of the cosmos. The death of our sun, the collision of the Milky Way with Andromeda, the slow fading of the last stars, the heat death of the universe itself, all from a few years of their subjective experience. But we are not here to hover. We are here to fall. And so we continue, past the point where light itself begins to struggle, toward the boundary that separates our universe from whatever lies within. The event horizon approaches. From outside, it appears as a perfect sphere of absolute darkness, not dark like a shadow or dark like the space between stars. Dark like an absence, a place where light simply does not exist. But here is something that may surprise you. Crossing the event horizon feels like nothing. There is no barrier, no wall, no membrane to pass through. You would not feel a jolt or hear a sound. One moment you are outside the event horizon, and the next moment you are inside, and there is no physical sensation to mark the transition. The event horizon is not a thing. It is a boundary, a mathematical surface that marks the point beyond which escape velocity exceeds the speed of light. Cross it, and you are forever separated from the universe you knew. But you would not know the exact moment it happened. Looking back, you would still see the universe, the stars, the galaxies, the light of creation, all of it compressed into an ever-shrinking circle above you, a window to a cosmos you can never return to. And here, something philosophically profound occurs. Every photon that falls into the black hole after you, every ray of light from every star that will ever shine, all of it is falling toward the singularity alongside you. In a sense, the entire future of the visible universe is compressed into that shrinking circle of light above your head. If you could somehow survive long enough, you would witness all the light that will ever enter this black hole, from now until the end of time, compressed into a single brilliant ring before you reach your destination. But survival is not in your future, because now a new force begins to make itself known. Gravity, you see, is not uniform. It is stronger at closer distances. Your feet, being closer to the singularity than your head, experience a slightly stronger gravitational pull. At first, this difference is imperceptible, but as you fall deeper, it grows. The pull on your feet becomes measurably stronger than the pull on your head. Your body begins to stretch. Scientists, with their gift for dark humor, call this effect spaghettification. Your body, once compact and whole, would be stretched like dough being pulled, longer and longer, thinner and thinner. The tidal forces that once lifted our oceans on Earth are now tearing you apart at the molecular level. For a stellar mass black hole, one formed from a collapsed star, spaghettification would begin well outside the event horizon. You would be torn apart before ever crossing that fateful boundary. But for a supermassive black hole, the horizon is so vast, so gently curved, that you might survive crossing it intact. The spaghettification would come later, deeper inside, giving you precious moments to experience the inside of a black hole. Moments that no one will ever hear about. No signal you send could ever escape. Your experiences die with you, secrets kept forever by the dark. You are now somewhere no human has ever been, somewhere no human may ever be. Inside a black hole. The universe you knew, the stars, the galaxies, the world of your birth, is now a single point of light above you, growing smaller with each passing moment. Soon it will be gone entirely, and you will be alone in the dark. What does space look like in here? Physicists believe that inside the event horizon, space and time exchange roles in a certain mathematical sense. The singularity is no longer a place in space that you might avoid. It is your future, as inevitable as next Tuesday. Just as you cannot avoid moving forward in time in the outside universe, you cannot avoid moving toward the singularity once inside the event horizon. Every path through space-time leads there. Every direction you might travel brings you closer. You might fire rockets. You might struggle. But like trying to stop time itself, you would only delay the inevitable by the smallest fraction. What would you see as you fall? The truth is, we don't know. Our physics breaks down as we approach the singularity. The equations that describe the universe, Einstein's beautiful equations of general relativity, produce infinities, numbers that climb without bound beyond any physical meaning. Some physicists believe that quantum mechanics, the physics of the very small, must somehow intervene. That space itself becomes foamy, uncertain, fluctuating at the tiniest scales. Others propose that the singularity is not a point at all, but a gateway, a passage to somewhere else. The mathematics of rotating black holes, which is to say, most black holes, contain solutions that suggest tunnels through space-time. Wormholes, paths that might lead to other universes, other times, other places entirely. Could you pass through? Could you emerge somewhere else, someone else, reborn in a cosmos you cannot imagine? Almost certainly not. The mathematics may permit it, but the physics almost certainly does not. The tidal forces would destroy you. The instabilities would collapse the passage. The universe guards its secrets well, and so you continue to fall, toward a point of infinite density and zero volume, toward a place where the mass of millions of suns has been compressed into a space infinitely small. As you approach, the tidal forces become unimaginable. Your atoms themselves are torn apart, electrons stripped from nuclei, protons and neutrons shredded into their constituent quarks. And then even the quarks are, what? Destroyed? Transformed? Compressed into pure geometry? We do not have words for what happens at the singularity because we do not have physics for it. The singularity is where our knowledge ends. What lies at the heart of a black hole? This is one of the great unsolved questions of physics, a question that has haunted scientists for a century, a question that may hold the key to understanding the deepest nature of reality. Einstein's theory of general relativity, our best description of gravity, tells us that the singularity is a point of infinite density, a place where space-time curves infinitely, a place where the math produces nonsense. But physicists do not believe in infinities. When a theory produces infinity, it usually means the theory is incomplete, that we are missing something, that there is a deeper truth waiting to be discovered. Many believe that the answer lies in quantum gravity, a theory that unites Einstein's relativity with quantum mechanics. Such a theory does not yet exist, though many brilliant minds work on it. String theory suggests that the singularity might be replaced by a tiny vibrating loop of energy. Loop quantum gravity proposes that space itself is made of discrete chunks that cannot be infinitely compressed. In these theories, the singularity may not be a point at all. It may be something small but finite, a core of unimaginable density but not infinite, a place where the universe has reached its ultimate compression, but not beyond physics. And then there is the mystery of information. Physics tells us that information, the arrangement of particles, the pattern of data, cannot be destroyed. It is one of the fundamental laws of quantum mechanics. But black holes seem to destroy information. What falls in is lost forever, reduced to three simple numbers: mass, charge, and spin. All the complexity, all the detail, all the history, apparently erased. This is called the black hole information paradox, and it has troubled physicists for 50 years. How can information be lost? Where does it go? Stephen Hawking discovered that black holes slowly radiate energy, a phenomenon now called Hawking radiation. Over immense timescales, black holes can evaporate, shrinking and eventually disappearing. Does the information come out in this radiation? Is it somehow encoded in the particles that escape? Or is it truly destroyed, and we must rewrite the laws of physics? We do not know. The black hole keeps its secrets. And yet, for all their mystery, black holes have taught us more about the universe than almost any other phenomenon. At the heart of nearly every galaxy lies a supermassive black hole. Our own Milky Way harbors one, Sagittarius, a star 4 million times the mass of our Sun, lurking 26,000 light-years away. These cosmic giants shape the galaxies around them. Their gravity influences the motion of billions of stars. Their energy, released when matter falls into them, can regulate star formation across an entire galaxy. In 2015, we detected gravitational waves for the first time, ripples in space-time created by two black holes colliding over 1 billion light-years away. Einstein predicted these waves a century earlier, and black holes proved him right. These collisions release more energy in a fraction of a second than all the stars in the observable universe combined. For a brief moment, the merging black holes outshine everything in existence, not in light, but in gravitational waves. And in 2019, we saw one. For the first time in human history, we captured an image of a black hole. Not an artist's rendering, not a simulation, an actual photograph. The supermassive black hole in the galaxy M87, 55 million light-years away. A ring of light surrounding a dark void, exactly as Einstein's equations predicted it would look. Black holes are not just curiosities at the edge of physics. They are laboratories, they are teachers. They show us where our understanding breaks down, and they point us toward deeper truths. Every mystery they present is an invitation. Every paradox is a doorway waiting to be opened. And so our journey ends, not with answers, but with wonder. We began this night as passengers on a small world, orbiting an ordinary star, in an ordinary galaxy, in a universe of 2 trillion galaxies. We are small, impossibly small. Our lives are brief sparks against the eternal dark. And yet, we are the universe knowing itself. We are matter that has arranged itself to ask questions about matter. We are stardust that wonders about stars. The black hole does not know it is a black hole. The singularity does not ponder its own mystery. Only we do that, only creatures like us, here on our small worlds, reaching out with mathematics and telescopes and dreams. Perhaps that is the deepest truth, that in a universe of darkness and gravity and endless void, consciousness has emerged, awareness has blossomed, the cosmos has opened its eyes, and on nights like this, we look up. We imagine falling into the dark. We ask what we would see, what we would feel, what we would learn, and even if we never go there, even if no human ever crosses an event horizon, we have already traveled so far, in our minds, in our equations, in our beautiful, fragile, wondering hearts. Rest now. Let your thoughts drift among the stars. Let the mysteries settle around you like a blanket. You are made of atoms forged in the hearts of ancient stars. You carry the universe within you, and tomorrow you will wake and the cosmos will still be there, waiting to be wondered at. Good night, traveler.